Okay, so here we're on to the next section, and now we're going to be solving exponential equations using logarithms. So we'll start with just looking at the review here. At the beginning of last chapter, when we had 4 to the x equals 2 to the x plus 3, we just wanted to write these as the same base. So we could write it as 2 squared to the x equals 2 to the x plus 3. So 2 to the 2x equals 2 to the x plus 3. Then, since the bases were the same, we could say that must mean 2x equals x plus 3 and solve for x. And you would get x equals 3. So that was simple enough. But now we get to equations where we have something like this. 2x equals 50. 2 to the x equals 50. So why can we not solve this one with the same method? Well, we cannot write 2 and 50 with the same base. That is impossible to do. So, determine by considering powers of 2, the two integers between the solution must lie. So we can come up with an estimate. If we know that 2 to the 5 is 32, and we know that 2 to the 6 is 64, that tells us that x will be between 5 and 6. Because we know that 50 is between 32 and 64. So estimating to the nearest tenth, well, maybe you say, well, 50 is a bit closer to 64, so I'm going to decide that this is going to be about 5.6. Now, the equation 2 to the power of x can be solved by taking the logarithm of each side and solving the resulting equation. So one way to solve this equation, just like we can do anything in math, if we do something to one side and we do it to the other, that is mathematically sound. So we can do the exact same thing with logarithms. If we take the log of both sides here, usually we use base 10, but really you could use any base. Then we use our power law to bring the x out front. So now we have x times log 2 equals log 50. If we divide both sides by log 2, we get x equals log 50 over log 2. And when we punch this in, we do get 5.6. So that is one way of using logs to solve an equation. The other way, you could solve one like this, is simply by changing to log form. So this is one method. The second one would be to say, well, I could rewrite this as log base 2 of 50 equals x. Type this in. You would also get 5.6. Both of these methods work for this question. For harder ones, this method won't do it. We'll need to introduce a logarithm to both sides. So solve the following equations expressing the solution as an exact value and to 3 decimal places. So here, we take the log of both sides. And again, I'm going to work in base 10, but in theory you could work in any unit, any base. It's just simplest to think in base 10. So we have x log of 4 equals log of 12. Divide both sides by log 4. So this is log 12 over log 4. This is a simple enough one. You probably could calculate it by just changing form up here, but either way works. B gets a little bit trickier. We now have this 4 here. So before we take the log of both sides, we want to make sure we have just our exponential function and another value on the other side. So we are going to start by subtracting 4 from both sides. Now we'll take the log of both sides, use our power law, and divide. Okay. So again, this one we could have solved using any method by switching form. We get to a different case here with C. This one, if we switch form, we have exponents on both sides, so that's a problem. So here what we need to do is, again, we're going to start by taking the log of both sides. Sorry, not base 3. Log of 3 to the 2x minus 1. We can now use our power law on both sides. Okay, now here's where this method gets a little bit tricky. If we divide things right away, we're left with this 3x over 2x minus 1, and that's a bit of a problem. So this gets a little bit more complicated. So here what we need to do is first expand out, whoops, what happened? Expand out, the smartboard's going crazy. Expand out here. What is happening? Expand out here. So we're going to multiply everything by log 3. So this side, there's nothing to expand. And now we have this. So now what we're going to do is anything that has a log in it, we bring to one side. Anything that has an x in it, anything that doesn't have an x, we bring to one side. Everything that has an x, we bring to the other. So in this case, this has an x, so we can subtract it from both sides. Just like we do whenever we have variables on both sides, we bring the variables to one side and the numbers to the other. Now what we're going to do is factor out the variable. So I can factor out an x from both sides here. An x from both terms, and I'm left with x times 3 log 6 minus 2 log 3. Now I can divide by this whole expression. So x is equal to the negative log of 3 divided by 3 log 6 minus 2 log 3. Now we can simplify this if we want. Sometimes they manipulate the answer using our logarithm laws further. We could bring those 3's up and the 2's up, use division to bring it together. Other times we're just going to punch it in and get the number. I'm kind of out of room here, so we're just going to type it into our calculators and get the value. Okay, we'll do D as well because these are getting pretty tricky here. So we have 2 log 3 times x minus 2 equals log of 7 to the x. So when I take the log of both sides, I cannot immediately bring that exponent down on this first logarithm here because the exponent is only being applied to the 3, not to the 2. So here I need to use my logarithm laws to first split it up. And on this side, I could bring the x down whenever I want. So now I'm ready. Sorry, this got kind of too big. Log 2 plus x minus 2 log 3 equals x log 7. Expand out. So I get x log 3 minus 2 log 3 equals x log 7. Now I'm going to bring the x's to one side and the numbers to the other. So both numbers are already on the left, so I'll leave them here. Subtract x log 3 from both sides. Gives me this. Left-hand side stays the same. Factor out the x on the right. Now I can divide by log 7 minus log 3. So there we have x, and again we could use our exponent or log laws to simplify it, but I'm out of room here, so we're just going to type this into our calculators, and we get negative 1.775. So the next example we covered already. So how is this useful to us? So here's an example. According to Statistics Canada in the 21st century, Canada's population has been growing at an average rate of 1%. The exponential equation P equals P naught times 1.01 to the n can be used to predict the population P n years after a known population. If the Canadian population at the beginning of 2001 was approximately 30 million, estimate in which year the Canadian population will reach 50 million, assuming the same average annual growth. So we have this equation here. We can substitute in what we know. So we know that we want 50 million here. That's what we want our final population to be. We know we had a population of 30 million. And our growth rate is 1%, so that gives us the value 1.01 to the power of n. So these functions or equations are easiest to solve when we first bring our constants together. So if we divide by 30 million here and do that to both sides, then we're going to have our exponential equation by itself. So we're going to have 5/3 equals 1.01 to the n. So now this is a simple equation. We could choose to take the log of both sides, or you could just change to log form. Either way works. So I took the log of both sides. Now I can bring the n down and divide by the log of 1.01. So when I take the log of 5/3, divide by the log of 1.01, I get 51.33 repeating. Now the question wanted to know in which year. So in the first year that I started with, it's at 2001, so I would take 2001 plus 51.333, and this would put me into the year 2052. So it's expected that in the year 2052, the Canadian population will be 50 million. We can take the logarithm of each side of any next exponential equation in any base, but it is simpler to use a calculator base. So most calculators work in base 10. You can change the base on yours, but usually you will see they're using base 10. So this is just a different example where they use the base of e instead, but the process is the same. Just like any other equation, you can also use your graphing calculator to help you, and it's especially good to check your answers with that. So we always have two methods. The intersection method is to graph the left-hand side of your equation in y1 or in f1, the right-hand side of your equation f2, and find out where they cross. That's your intersection method. Or the zero method is to bring everything over to one side, have one side of the equation equal 0, and find where your x-intercepts are. If you need help solving graphically, come and talk to me, but most of you are probably pretty confident with that.